Hi all, this is a quick chat on the subject of Earth as a planet. And as I recall, I I didn't have a lot of instruction going that one because of 4th of July. So I hope that for now you are seeing my screen and you're hearing my voice. And this is chapter 8, Earth as a planet. And I think on Monday, on the chat on Monday, formation of solar system, and the one on Thursday, I went and I covered some of the subject, but basically, Earth is a planet, and as a planet, it has to be treated as any other planet as far as its geology, its formation, its origins, and the type of transformations that go through. As I always like to do, I like to see the end content of a chapter, and those are the key concepts. Key concepts in summary. So look at Earth. Earth is part of the terrestrial group of planets, and when you look at the history of all terrestrial bodies, those that don't have a lot of a transformation, surface transformations, they happen to be more likely, apparently, looking like what they were in their very beginning. So the solar system went through a area of bombardment that lasts from 4.4 to 3.8 billion years ago, where planetesimals and planets were being formed. And, and so the terrestrial planets in this bombardment time got several collisions, giving rise to a surface that is pretty much punctured by several craters. Now, in the case of Earth, these craters have disappeared, in part because we have a vigorous hydrological cycle that washes out indicators of collisions of craters. So we have erosion and we have weathering of minerals associated with impact. But more primarily, Earth also has plate tectonics. Earth is a geologically active planet in, in which its surface is covered by 12 or more major plates that have independent motion. So some of these plates move against one another, some of these plates move apart from one another, some of these plates pass one another. And depending on the type of interactions they have, features such as volcanoes, mountains, and trenches, and earthquakes, and all these um, mountains range like Himalayas and Appalachians that were formed when two continents, rocky continents, collide, or islands like Japan that were formed when ocean floors collide with one another, or Andes that happen when a plate collides with a continental, oceanic plate collides with a continental plate. So those different features are the result of the geology Earth goes through. Um, Here's an example of collision that still exists, not so far away as far as time is concerned, 50,000 years ago, which is pretty much recent to our history. We have this big impact that happening in Arizona. So the impact that is still available to visitors to go and see it. Meteor crater in Arizona. That's a nice example. It's still there because the region is a desert, doesn't have a lot of erosion taking care of it. Chicxulub is another indicator of uh, collision that happened on Earth 65 or so million years ago. And this impact was so magnificent that is associated with the end of the dinosaur era, in which the collision produced so much dust and powder in the atmosphere that covered Earth with this thick layer reflecting sunlight and bringing the planet to a cooling process for several years. And as a result, these big animals couldn't adapt to the sudden change, and and then they disappear. And those other animals capable of surviving the transitions, they were able to adapt and to evolve in this hostile environment. Now, let's take a look at Earth crust. So Earth crust, as I mentioned, there are several indicators of the, the activity we go through. Rocks can be classified as sedimentary, igneous, or metamorphic, but primarily you might be able to identify igneous rocks, quite often associated with volcanic activity. Like if you go to Hawaii Island, the rocks are volcanic and are associated with volcanic activity. Why is that? Well, there is a hot spot that is shooting out lava in that region and forming islands as we speak. So plate tectonics is a theory by which Earth is divided in several 12 or more major plates, and because of the relative motion of these plates and their collisions, features such as volcanoes, mountains, and all of that can be detected and are formed here on Earth. So also the oceans are covering a floor that is relatively young, no more than 200, 300 million years. And the reason for that is in the middle of the oceans, Atlantic, Indian, Pacific, and Arctic oceans, it goes a system of rift valley, which indicate two plates parting or departing from one another. And in fact, if you go and look at the eastern part of the African continent, the northeastern part, there is a rift occurring in that region, and as the rift occurs, water takes place. So oceans are, when this rift occur and persists, then water takes place, and then you ended up with the sea, and maybe you ended up with the ocean if the motion doesn't stop there and just keep on moving and going in the same direction. But in this picture here, you can see the most of the major plates and their relative motion. So here indicate plates moving apart from one another in the ocean. If you look here in the North America, San Andreas is the interface between two plates that pass one another, and Juan de Fuca plate, which is somewhere here, is not being shown, is the one responsible for the formation of all the volcanoes we are so familiar, and part of the Cascade range of volcanoes, North California, Washington, and Oregon. So volcanoes or range of volcanoes is formed when one active plate collides with another plate and a phenomenon called subduction takes place. Here's the idea of a rift valley with two plates moving one another and magma pretty much filling in the gaps. And then you have volcanoes around it. Now, when a continental plate collides with an oceanic plate, the oceanic plate, because it's heavier, it's denser, it's thinner, as you can see here, this is thinner than this one, but it's heavier because it's formed of a heavier mineral. So that slabs sink down, and we call this subduction. And as a result of the slabs sinking down, bringing sediments with water, with moisture, this water and moisture, in fact, reduce the melting point of the mantle, and then it melts. So the rocks melts. So rocks in the mantle are not melted; they are just hot. But once they are exposed to humidity, basically, their melting point is reduced, and then it melts. And as it melts, it bubbles up because the density is less, forming a chain of volcanoes, subduction zone, and San Andreas, which we are pretty much aware of it. I recommend, if you wanna. Years ago, Chrome 4 News released a series of, in fact, was a show, was 1 hour show, a science report on San Andreas in the Bay Area, and I really recommend you to see it. It's not outdated at all. It's very well done. Let's see if I can find it here. It's called the fault line, I think. No, who is the fault? Oh, where is the fault? Chrome for news. Maybe YouTube. Yeah, well, I can find. If you ask me to look, I can get it. I thought I had that. Perhaps I have the wrong name. Chrome 4. Yeah, I can find it. Anyway, I will look for that. Don't know what it is right now. So associated with this geologic activity, plate tectonics, mountains. So mountains like this, formed by glaciers. So here, this carving part. These mountains are the result of the interaction of hydrological cycle or plate tectonics. These mountains are raising up because of plate tectonics, but also earthquakes. And earthquakes are the result of generated waves or energy from points where these plates are being stick together, but the energy is such that they are forced to move, and when they move, they release energy, and this energy is it goes in waves, and we call that seismic waves. Now, these seismic waves, they have an important factor in our understanding of our interior part, and the reason is there are three major types of waves that comes out of a volcanic an earthquake. One is the P waves, or compressional waves that can pass through solid, and shear waves or secondary waves that don't pass through liquid phase, and surface waves, which are the most devastating ones. So P waves are the fastest, and then secondary waves are the second faster, and then the surface waves are the last one to arrive, but they are destructive. Seismographers astronomers or geologists to measure these waves. But since shear waves or secondary waves don't go through liquid phase, it was found that Earth has a shadowy region in which these seismic waves don't go through, and because of that, it was found that our planet Earth has a liquid interior part. That's how we know that the core of our planet Earth is divided into regions. One is solid, is the central core, and another part of the core, the external one, is entirely liquid, and these S waves don't go through. So I would say those are the main aspects of this chapter. The atmosphere also has important components with respect to composition. Nitrogens are the most abundant gas in the atmosphere, and oxygen is a byproduct of life in our planet. I guess that's it. If you need some more explanation on this chapter, don't hesitate to contact me, and I try to squeeze in some more detail tonight in our chat room.